Okay, let's jump right into some exercises about logarithmic functions. This first one is number 5 in the textbook, and it asks us to simplify the expression completely. Now, let me start out by saying that it's not always obvious when one expression is simpler than another. Sometimes it's a little bit subjective. But what they mean in this case is this quantity here, we'll see, can definitely be simplified. And this quantity here, we can split apart using one of our log rules. So jumping right in, we've got two different parts that we need to simplify. This ln, remember ln here is the natural log, so that's the log base e of 1 over e. So this is like saying, this quantity says e to what power equals 1 over e. Whatever the answer to that question is, that's what that quantity is. It's the thing that if you raise e to that thing, you get 1 over e. Well, of course, how do we get 1 over e by raising e to a power? It's just e to the negative 1. Raising anything to the negative 1 power just takes the reciprocal. So this part here, this natural log of 1 over e, that's just a negative 1. Now for the other part, this part here, we have one of our rules of logarithms that says if you have multiplication inside, that becomes addition outside. So that part, the natural log of a times b, becomes the natural log of a plus the natural log of b. That's multiplication inside becoming addition outside. So what do we get when we combine those? The first part becomes negative 1 plus the natural log of a plus the natural log of b. And that's what we get when we simplify. Now, like I said, it's maybe a little bit subjective. Why is this simpler than that? For starters, this is longer, so why would it be considered simpler? That is a little bit subjective, but normally what they mean when they say to simplify is to apply whatever rules you can to take any unknowns, in this case a and b, and make them separate from each other as much as possible. On to our second question. This one asks us to solve for x using logs. And what makes this a little bit tricky is that we have two different bases. This is 7 to a power, this is e to a power, and we have x in both of the powers. So there's a couple different ways that you can go about this one, and you will get answers that look different, definitely very different, until you plug them into a calculator and you see that they're the same. But as always, if we want to solve for x, that means we need to somehow isolate the x's, and since they're both in powers, we need some way to remove them to bring them down from the exponent. Now you might think, well, I'm stuck because this one is a 7, so I would need a log base 7. This one is an e, so I would need a log base e, or a natural log. But actually, that's not the only way to bring things out of a power. We have this one rule that says log base anything of x to the y. So you have this power in the log. That can be brought out front as a constant multiplier, y times log base a of x. So what that actually tells us is that we can get these x's out of the power and down in front as a multiplier using any log base. So you could use 7, or you could use e, or you could use something that's different. You could use log base 10. Any log is going to work. So let me start by, let me do this two ways. The first way I'll do it will be using log base 7, just as an example. So let's take the log base 7 of both sides. Now, for both sides, well, okay, on the left-hand side, what we could do is realize that we've got a log base 7 and a 7, and that those are operations that cancel out. Those are inverses because the 7 matches the 7. So that becomes an x plus 2. Now, on the right-hand side, that trick doesn't work. Log base 7 does not cancel out e. But we still have this property that says the 17x can come out front as a multiplier. So that becomes 17 times x times log base 7 of e. Now this quantity will be some number. There's no x's in here. We don't know what it is without a calculator, but it's some number. So what do we want to do? This would be a really common place to get stuck. Well, we want to solve for x. So what we do now is we take all of the terms with an x and try to get them on one side, and all of the terms without an x on the other side. If you remember that little sentence, that's going to always help you. Get all the terms with an x on one side, because then you can factor it out. Get all the terms without an x on the other side. So let's move this term, it's one big multiplicative term, with an x over to the left, and then this term, the 2, we'll subtract it over to the right. So this is x minus 17x log base 7 of e equals negative 2. And then because all the terms on the left-hand side have an x, we can factor it out. When we factor x out of x, that leaves 1. When we factor it out of the other term, that's 17 times log base 7 of e. And the whole reason that this was a good thing to do is that now we have x times a constant. Again, we don't know what it is without a calculator, but it's a constant, so we can just divide it over. And so we get our answer, at least in symbolic form. X is negative 2 divided by 1 minus 17 log base 7 of e. So you could plug this into a calculator and you'll get, let me see, I have it written over here somewhere. You'll have about 0.2585. Now, of course, your calculator does not have probably a log base 7 button. So the way you calculate log base 7 of e is using that change of base formula. You use any base, either log base 10 or natural log, whatever you like. And you say log of e over log of 7. And that's how you get your log base 7 of e. Okay, now this was with taking the log base 7 of both sides. But any base works. So let me repeat the work, but with a different base to start with. So let's suppose instead that we took the, let's say the natural log of both sides. So that's the natural log of 7 to the x plus 2 equals the natural log of e to the 17x. Then we're going to follow the same kind of steps. On the right-hand side, the natural log and the e cancel. That leaves us with a 17x. On the left-hand side, we've got a power, and so that power can come out as a constant multiplier, just like this rule right here says. So that gives us x plus 2 times the natural log of 7 equals 17x. And now we need to do the same kind of thing. This isn't really an x times natural log of 7 plus a 2 times natural log of 7. So it's an x natural log of 7. I'm going to bring the 17x over to the left with a minus. And then we also had a 2 natural log of 7, which I'm going to bring to the right with a minus. I'm kind of skipping over a few of the steps here because they're so similar to the other side. And then lastly, we factor in x out of both of them. What will be left is natural log of 7 minus 17, and we divide that over here. So just because I'm a little squeezed for space, let me write that all in one step. We get x equals negative 2 natural log of 7 divided by natural log of 7 minus 17. And again, that looks very different from our other answer, but if you plug it into a calculator, you should get the same thing. Now, in these two examples, I used either log base 7, because we have it at 7 here, or a natural log, because we had an e here. But you could once again do the exact same thing with log base 10 or log based 123 or any log. You'll get something that looks slightly different, but it will be numerically the same thing. Moving on to our third problem now. This one gives us an exponential function, and it wants us to put it in this form. Now, this is a form that we saw in 1.2. It's a an exponential form, but it's a little bit different because it has this k times t. So we talked about how to put anything in the form e to the kt. The advantage is that when you have a base e in the exponential, we'll see later that that's useful for a lot of things. And you can always do that if you're allowed to cheat a little bit by putting a k in the exponent. Okay, so the way that we need to do that is with a natural log. So we want this 15 times 1.5 to the t to be equal to a p0 times an e to the kt. Well, the way that we saw to do this in section 1.2 for starters is that this 15 becomes our p0. So that's our easiest part. So that means we have a 15 here and a 15 here that we can both divide them away. And what we're left with is that 1.5 to the t has to equal e to the kt. And we're solving for k here. So we're kind of in the normal situation where we've got something we want to solve for, the k, in the exponent. And so the way that we bring it down is with a natural log. So let's take the natural log of both sides. That says the natural log of 1.5 to the t equals the natural log of e to the kt. So on the left-hand side, we can use that trick again where any exponent inside can come out front as a constant multiplier. In this case, it's a variable, but a multiplier. So that's t times the natural log of 1.5 equals. Over here, we have natural log of e to the something. So natural log, that's taking, well, in this case, the e is the inside, so that's take the exponent, and then the inverse is take the log. And so you end up with what you started with, which is a k times t. And here, both sides are multiplied by t. So we can divide that out, and we're left with exactly what we wanted, which is a solution for k. K is the natural log of 1.5. Now on exams, I would just have you leave it like this, because you won't have a calculator on your exam, so obviously you can't calculate something like natural log of 1.5, but usually Wiley Plus wants a numerical answer. So if you go to your calculator and you plug this in, you're going to get that it's about 0.4055. So our final answer, putting the function in that form, is that p equals 15 times e to the 0.4055 t. So all we really had to do was set our multiplier to be the same thing, the 15, and then solve for the k. That kind of made the 1.5 and the e line up. The difference between the 1.5 and the e is this power. Okay, hopefully that wasn't too hard. On to question number 4. The size of an exponentially growing bacterial colony doubles in 5 hours. How long will it take for the number of bacteria to triple? So what we need to do here is write out a formula first for the exponential growth that may or may not require some logarithms, and then let's figure out how long it takes to triple. So the size doubles in 5 hours. So let's think about what that means. Let's suppose that you start with p0 size, whether that's the size by the number of bacteria or whatever else. You start with p0. Now, after 5 hours, I just want to summarize this in words before we try to put it in a formula. After 5 hours, it doubles. So that means we have 2 times p0. So let's think about what our population grows like. So we know we're going to have an exponential function. We just know that because it says exponentially growing. We know we start with some number. Now the easiest way to figure out how to write this is to not start by saying, okay, if it doubles in 5 hours, what does it do per 1 hour? You could think about it like that, but the way I like to think about it is I know it's going to double in some amount of time. So let me put the 2 for doubling, and the question then is what goes up here. So if I were just to put t, that would not be right. That would make it double every 1 hour. but we want to double every 5 hours. So here's the trick. Instead, we can make it t over 5. So let's think about that. Dividing by 5 is like saying that every time the exponent goes up by 1, the number of hours goes up by 5. So for example, p of 5 is p of 0 times 2 to the 5 over 5. So that's 2 to the 1. So this says after 5 hours, the amount we're left with is double, 2 times p0. After 10 hours, the amount we're left with, the amount we have is p0 times 2 to the 10 over 5, which is 2, and that's 4 p0. And this was, let me just write 2 p0. So doubled after 5, and then after another 5, we doubled again, and if we put in 15, we would get 8 p0, and so on. Okay, so that's a nice way to think about writing the formula. Now, what are we actually calculating? We want to know how long it will take to triple. So this is an inverse problem because now we know the output. We want it to be 3 p0, and the question is, what does the input have to be? So that means we're solving the equation 3 p0 equals p of t. So we're solving this for t. Let me rephrase that. What time do we have to plug in? How many hours to get triple? Well, we should have a little bit of an idea. After 5 hours, it's double. After 10, it's quadruple. And triple is between, right? That's 2 times and 4 times, and we're looking for 3. So whatever we get should be somewhere between 5 and 10 hours. So let's plug in the formula that we just found. We have 3 p0 equals p0 times 2 to the t over 5. We can divide both sides by p0 so they cancel. That gives us 3 equals 2 to the t over 5. And now we need a way to solve for t, but it's the same trick as always. We've got a t in the exponent, and we don't want it in the exponent because we want to solve for it. So we'll take some kind of log of both sides. Now, just like before, you could use any base because any base will let you use that trick where you take the exponent and bring it in front as a constant multiplier. But in this case, since we have a 2, might as well just use log base 2. So that tells us that log base 2 of 3 equals log base 2 of 2 to the t over 5. Let's come up over here to finish our work. On the right-hand side, the log 2 and the 2 cancel. So that's log base 2 of 3 equals t over 5. And lastly, we're going to multiply that 5 over to get t equals 5 times log base 2 of 3. Now, once again, on an exam, you would just leave it like this. And sometimes Wiley Plus will ask for an exact answer, which means you just put it in like this instead of a numerical approximation. But because the book usually likes numerical approximations and because that's what the solutions are usually stated at, if you were to plug this into a calculator, I'm just saving some time, I did it ahead of time, you should get 7.9248. So again, this would be a good chance to test that you know how to do this in a calculator. You probably don't have a log base 2 button. You probably need to use the change of basis and do log of 3 divided by log of 2. So it's a good chance to check that you can do that and get this. And by the way, we said we were expecting something between 5 hours where it doubled and 10 hours where it quadrupled, and that makes sense. It takes about 7.9 hours to triple. Okay, we have one final question here, and this one will be a quick one, I think. This is number 61 in the book, and they give us graphs with 4 functions. And they say that the 4 functions are these for e to the x, natural log of x squared, and x to the 1/2. And they want us to identify which is which. And obviously, we don't have much information here. What we do know is that a and b are increasing fast, c and d are increasing slow. And we also know that b and c cross the point 0, 0, whereas a and d do not cross the point 0, 0. So those are the bits of information that are going to allow us to separate these 4 functions into the right type. So let's look at these 4 and say which ones grow fast. Whichever two grow fast will have to be a and b. Well, e to the x grows fast because it's an exponential. And x squared, we haven't seen too much about these powers in polynomials. We're going to see that in, I think, 1.6. But you know probably what x squared looks like, roughly like this. So e to the x is exponential. It grows way, 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 way faster than any polynomial, but a polynomial still has this kind of shape. So a and b are probably those two. Now, we should never assume that our graphs are exactly to scale. So in figuring out which one is which, it's probably not a good idea to say a is growing faster, so it must be e to the x. Instead, we can be more concrete by looking at where a and b have their y-intercepts. A has its y-intercept there, not at the origin, not at 0, 0, and b does. Well, if we think about x squared, we look at this picture right here. X squared crosses 0, 0. On the other hand, e to the x has its y-intercept at 0, 1. That's something that we saw on the graph. And the reason we know it, just as a reminder, whenever you're saying that a point is on a graph, that always means if I plug in the x point, I should get the y point. So in this case, e to the 0 equals 1. So this here, that must be the point 0, 1, but that's the point 0, 0. And so this tells us that a is e to the x, because it grows quick and it crosses not at the origin, and b must be the other fast one, x squared. We'll use the same kind of analysis with the other two. We're trying to decide between natural log of x, which grows kind of slow, and x to the 1/2, that's the square root of x, which also grows slow. So let me remind you, whenever you see something like x to the 1 over, let me say, k, that's just another way to write the kth root of x. So x to the 1/2, that's the square root. X to the 1/3, that's the cubed root, and so on. So they both grow slow, but their difference is that c crosses at the origin right here, whereas d doesn't. So what does the natural log of x do? Where does it cross the x-axis? Oops, that should be has. It has its x-intercept at 1, 0, and this is because the natural log of 1 is 0. If you go back and you look at our graph for the natural log of x, that's what it looks like. If you were to keep drawing it, it kind of goes like that and has an asymptote. So that means d must be the natural log of x because the natural log does not cross through the origin like c does. So d is the natural log of x, and that means c must be x to the 1/2, or the square root of x. Now why does that go through the origin? Because the square root of 0 equals 0. So that means 0, 0 is on the graph of the square root of x. Okay, so I like questions like this because they don't require a bunch of numerical calculation, but they're really testing conceptual questions. The book usually puts questions like this towards the end, and there's especially a last section where it will give you a bunch of false statements and say, why is this false? I think once you've gotten good at some of the numerical calculations, those questions are really, really useful for testing your knowledge because they force you to think conceptually. And once you can master those questions, I think you'll be in good shape. Okay, that's it for the 1.4 exercises.